Okay, so we are going to talk a little bit about error propagation and uncertainty, since that is something that we will be dealing with quite a bit in this lab. In general, we can characterize, or we can do error propagation in a couple of different ways, but they all come down to doing this derivative or partial derivative form down here in the box, where we're after the uncertainty in some value f. And that uncertainty is represented by a delta, so we have delta f. The square of that uncertainty depends on how f varies with the different variables that go into it, so x, y, z, whatever those happen to be, and their uncertainties, so the uncertainty in x, the uncertainty in y, the uncertainty in z. Now if we know the form of our function, be it addition, subtraction, multiplication, division, natural log, anything like that, obviously those functional forms are set, and we can come up with the uncertainty. We can do that derivative in advance. We don't have to do it for our actual measurement, although you are welcome to, certainly. So here I have on this slide summarized a decent number of uncertainty propagation steps. So the uncertainty in f for addition subtraction is just going to be the square root of the uncertainty squared in x and y and z and whatever other components we have. In this slide, a and b are going to be numerical constants, and then x and y would be the things that you would be that you would have uncertainty in, or that you would have error in, that you want to propagate. So for addition subtraction, it's the square root of the sum of the squares, or of uncertainty. For multiplication division, it's the square root of the sum of the relative uncertainties. So we have to interconvert between relative uncertainty and absolute uncertainty. And then we have some other special ones. So we have exponentials, we have natural logs, and the uncertainty delta f in all of those. So let's look at an example for how some of these will work. So let's say we are going to make a solution of sucrose and water, and we want to know the uncertainty in the concentration. We're going to start by massing some sucrose, and because we want to get a little bit more experience doing the uncertainty propagation, we're going to do our massing in a stupid way. We're going to tear a beaker and put 120.25 grams of sucrose in it, and then we're going to add additional sucrose to that. Experimentally, completely bizarre, but we'll just go with it. So the stated uncertainty in the balance, if you read on the balance, is 0.01 grams. That matches what we would get from the reading, right, the last digit. So our total mass of sucrose is going to be 185.23 grams. That uncertainty, because we're doing two different massings, depends on the uncertainty of each massing step. So our addition subtraction form in this case is going to be f is ax plus by, where a and b are just constants, x and y are our measurements. From the previous slide, that uncertainty in f then is the square root of the sum of the squares of the uncertainties. So f is the value, so that's going to be 185.23 grams that we get by adding 120.25 and 64.98. X is 120.25, y is 94.98, right? So we're just substituting into that addition form. A and b are constants, they're both 1 in this case, we don't have any multipliers. The uncertainties, delta x and delta y, come from the balance, so they are 0.01 grams. So now we just plug in, and we get a delta f, an uncertainty in f, of 0.014 grams. So the mass of sucrose that we have at the end, assuming we transfer completely accurately and everything, is 185.23 plus or minus 0.014 grams. So we have a mass of sucrose. But remember, we're after a concentration, so we're going to take that mass and dissolve it in 10 mils of water. And we're going to use a graduated cylinder because we don't know what we're doing. And it's graded in milliliters, and our uncertainty in volume is 0.1 milliliters. So we're pouring this almost 200 grams of sucrose into a 10 mil graduated cylinder. Don't try this at home. So we want a concentration. We have a mass. That means we need moles. So before I can even worry about calculating the concentration, I need to convert my mass of sucrose to moles of sucrose. So I'll use the molar weight, or the molecular weight. That math gives us 0.541139 moles of sucrose. The way we did that was multiplication division, right? We took a mass, we divided by the molar mass. So that's AXY, or AX over Y, or X over AY. Doesn't matter. The form of the uncertainty is the same in either case. It's the sum of the squares of the uncertainty divided by the square of the value. So relative uncertainties in this case. We can solve that for delta F, the uncertainty in F. F is our final value, 0.541139. X is going to be the mass, so 185.23. Delta X, the uncertainty in X we have is 0.014. Y is our molar mass, 342.29685. And as is often the case, we're taking the molar mass to be known absolutely. So we're assuming no uncertainty in the molar mass or the molecular weight. Sometimes you will see uncertainties given, maybe the last significant digit is given, but we're just going to take it as having no error whatsoever. So that makes the math very easy, and our uncertainty in the number of moles is 4.09 times 10 to the minus 5 moles. So there we go, 0.541139 plus or minus 4.09 times 10 to the minus 5 moles of sucrose. Now we can do the actual concentration calculation. So we're going to take our moles, divide by liters, so 10 milliliters in liters, to give us 54 molar, not surprisingly very high. This is another multiplication division. Delta X is the uncertainty in the moles. Delta Y is the uncertainty in the volume. That gives us an uncertainty of 0.541139 molar, so we can write that out. Most of those significant digits don't really matter in the uncertainty, though, so it's best reported as 54.1 plus or minus 0.5 molar sucrose, which, if you think about it, is about 1%. So why do we have that 1%? Well, if we look at the relative uncertainty in the moles, it's very, very small. If we look at the relative uncertainty in the volume, it is 1%, basically. And the bigger errors tend to dominate. So if we have a 1% error in the volume in our last step of the calculation, that is going to overwhelmingly contribute to the point where it washes out the uncertainty in the mass. We went through this step by step. That is definitely the clearest way to think about it, to work through it, to go through and for every mathematical operation you do, propagate the error. You can set it up in Excel if you want to. Sometimes that's helpful. You could also write out absolutely everything as one gigantic formula and then do the derivative expression from the first slide of that formula. And there are a variety of sources for where to find the uncertainty propagation steps. So obviously you have this slide, but that slide was taken from the PChem textbook, right, or the PChem lab textbook. But there are plenty of places to get the kinds of formulas and examples to do the error propagation.